For this complex, if you will check the hybridization, student, this complex where triphenyl phosphine, this PPH3 is called triphenyl phosphine and it is present 3 times. And please remember triphenyl phosphine have density of 1. So triphenyl phosphine will form 3 coordinate bond, and again it is heteroleptic complex. This is Cl, which is density 1. So coordination number for this complex should be 4. 3 coordinate bond will be formed by triphenyl phosphine and 1 coordinate will be formed by chlorido. This is the central metal, it is rhodium. It's very important compound which is referred as Wilkinson's catalyst. In this case, if you will see, rhodium, which is, I can say, it is the metal of the lower transition series. When I am saying lower transition series means what? You should understand there are 4 transition series, student. If you talk about this is 3D series, it is first transition series and it takes place from scandium to zinc. When I'm talking about 4D series, that is second transition series, it is yttrium to cadmium, and 5D series, that is third transition series, that is lanthanum to what? Mercury. So generally we refer these two series as what? Lower transition series. So if the complexes are formed by lower transition series, please remember as we are moving down in the group, then the size of the metal increases. Since they have larger size and they have larger surface area, so they can hold ligand into the same plane. So if there is second transition series or third transition series element, I mean if it is the element of the lower transition series and if the coordination number is 4, then generally the hybridization is what? DsP2. Now we all know that if the coordination number is 4, then the type of hybridization, it can be sp3 or it can be dsp2. But if the metal is present from the lower transition series, student, then it is not sp3, it is dsp2. The reason behind this, the size of the metal. Since the metal is taken from the lower transition series, so the metal is what? Large. So for all large metal atom providing larger surface and they are able to form planar complex, and for all planar complex, that is square planar complex for coordination number 4, the hybridization is what? DsP2. If central metal atom is large, that is like platinum, palladium, rhodium, that is if they belong to second transition series, that is 4D, or third transition series, that is 5D, then you can see because of the larger size, can you compare this? This is the tetrahedral complex. This is coordination number 4 and the hybridization is sp3. And this is the coordination number 4 but the hybridization is dsp2. If you will compare the size of the metal, here the metal atom is what? Smaller. Generally it is from the first transition series, and here if you will see the metal atom is very large. Because of the larger size of the metal atom, it provides larger surface area, so it can hold all ligands into the same plane without any steric hindrance. So large metal can arrange large ligand on plane easily, but small metal atom cannot arrange them, so the complex is never planar. You got this? So basically when the coordination number is 4 for these metals, lower transition metal, then always the hybridization is dsp2, and the reason is their large size of the metals. Some examples if you will see over here. These are the two compounds. So first you check the type of complex. Student, these both are anionic complex. There is negative charge. One is homoleptic. There is only one type of ligand, that is chlorido, and another is what? Heteroleptic complex. So for this, if you will check, the central metal atom is same, that is platinum. Now platinum should be taken from the lower transition series, that is third transition series, So the size of the atom is large. If you will check the coordination number, their coordination number is 4 in both the complex. So the configuration for this is what? Planar, that is geometry is planar, and the hybridization will be DsP2. So the reason behind DsP2 hybridization is what? Larger size of the metal. Because of the larger size, these metal can hold the ligand into the same plane without repulsion between the ligand. So please remember this note. If central metal atom is large, then irrespective of strong field or weak field ligand, it will always be planar. Got this? Now, there are certain limitations of the BBT. If you will see, student, for this complex, we have written hexacyanide manganate 3 ions. If you will calculate the oxidation state of the manganese, it is +3. Normally, manganese in the ground state have configuration of 4s to 3d5. But when the manganese is converting to manganese 3 plus, there has to be loss of 3 electron. So 2 electron will be lost from 4s and 1 will be lost from 3d. So 4s will become vacant and 3d will become what? 4. Student, if there are 4 unpaired electron, you just check the nature of the ligand. The nature of the ligand is what? Strong field ligand. So what is the role of strong field ligand? Strong field ligand must cause the pairing of electrons. So these all 4 electrons should paired up and there should not be any unpaired electron. So its unpaired electron should be 0. Its magnetic moment should be 0 and this complex should be diamagnetic as per BBT. But if you will see, experimental result is different from this. If you will check this value, experimentally it has been seen that the value of magnetic moment is root of 8. Means if it is root of 8, so it must contain how many unpaired electron? Yes, it is 2 unpaired electron. So the presence of 2 unpaired electron is not explained on the basis of what? BBT. So BBT fails for explaining magnetic nature of some of the complex. Another example, if you'll see, this complex is called tetraamine copper 2 sulfate. So this tetraamine copper 2 sulfate, which is deep blue in color, it is also called as cupra ammonium sulfate. Please remember, the common name of this complex is cupra ammonium sulfate. Now what is the coordination number? The coordination number is 4. It's a homoleptic ligand because the density of the ammonia is 1. So for 4, either it should be sp3 hybridization or dsp2 hybridization. Student, this copper metal belongs to the first transition series. It should have got smaller size. So it should have sp3 hybridization. But it has been found that the hybridization of this is for dsp2. So explanation of dsp2 is not properly given by what? BBT. If you check this, this is copper 2 plus, when there has to be loss of 1 electron from, initially if you write copper configuration, so it is 4s1 and it is 3d10. So copper 2 plus, it is 4s0 and 3d9. If there is 9 electron, there has to be 1 unpaired electron. If the coordination number is 4, so it should require 4 vacant orbital. So 4 vacant orbital means we have to take orbital, 1 orbital from 4s and 3 orbital from 4p. So if we take 1 orbital from 4s and 3 orbital from 4p, then the total vacant orbital should be 4. And this 4 ammonia should give 8 electron, and this 8 electron should accommodate into this valence orbital. But if you will see, there has to be sp3 hybridization as per BBT. But the observed case is what? This unpaired electron jumps to what? 4p orbital. So there is 1/2 4p orbital, and 1d, 1s and 2 orbital is involved. So this hybridization is what? It is dsp2. The hybridization is dsp2 hybridization in this case. Also some points it will see. Valence bond theory gave variation in the magnetic moment of the following configuration. If it is d4, d5, d6 and d7, then the magnetic field, the magnetic moment for the strong field ligand have what? Variable magnetic moment. So this is not correctly explained on the basis of what? VBT. So the conclusion, if you will see the limitations here, we can conclude that as per VBT, some following points which is not applicable for all the complexes. The very first, it cannot explain the spectral properties like colors of the given complex. Color of complex is explained on the basis of CFT. That is the next theory. It does not explain magnetic moment arising from orbital motion of electron. It cannot explain why some complexes are inner complexes and some complexes are outer complexes of same metal ion in the same oxidation state. It cannot explain correlation of the magnetic behavior based upon the geometry of the complex. It does not distinguish between weak field and strong field ligands. And also, it cannot predict exactly the tetrahedral and square planar structure of coordination 4. So these are the above following limitations of the valence bond theory.